Humanity, enveloped in entropy, desperately seeking symmetry for peace of mind. Dean Kavanagh. I have no idea what that means, but thanks, Internet. That's right, today we're talking about enthalpy and entropy. Hit the theme!
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu coming at ya. I'm your host Fu, and with me as always is Shu.
Shu know it.
So Shu, entropy is a term we've already discussed this year. Last lesson we talked about how energy is involved in chemical reactions.
Yeah, and in today's episode we're going to talk about how entropy and energy can be used to predict whether a reaction will occur or not. So let's get started. Enthalpy and entropy, a lesson from the kinetics and equilibrium unit. Enthalpy change, delta H. The enthalpy of a chemical reaction is the same thing as the heat of reaction. Systems in nature tend to move towards lower energy since there is an increase in stability. For this reason, exothermic reactions are favored in nature as the products are at a lower potential energy than the reactants.
Entropy change, or delta S. Entropy is the amount of disorder or randomness found in a system. Remember, gases have high entropies and solids have low entropies.
Oh, I remember.
Systems in nature tend to move towards high entropy, since the entropy of the universe is always increasing. This is the second law of thermodynamics.
So systems in nature tend to go to a lower energy and a higher entropy. A nice way to remember this is to picture your bedroom. Let's say your mom just got you to clean your room, everything's nice and organized and put away. Well, what's gonna happen naturally over time? Your room's gonna become a huge mess. So how does that help you remember what happens in nature? Well, everything that you hung up on a hanger or a book that you put on a shelf is gonna end up all the way on the floor. So that represents going from a high to a lower energy over time. Also, everything's completely random and all over the place. This represents the entropy increasing.
Another aside here, guys, and you gotta promise you didn't hear this from me. But if your room ever gets really messy, you can just say, "Hey Ma, my other mother, Mother Nature, she wants my room to be messy."
Table I, heats of reaction at 101.3 kPa and 298 Kelvin. By the way, if you see a question that specifically references 101.3 kPa and 298 Kelvin, they're probably wanting you to go to Table I. Various chemical reactions and their enthalpy changes are listed on Table I. Notice the asterisk at the bottom? It says the delta H values are based on molar quantities represented in the equations. A minus sign indicates an exothermic reaction.
We can't emphasize this last bullet point enough. If you look at the bottom of table H, that asterisk, it's literally telling you what a positive or negative delta H means. We already covered this in potential energy diagrams, but a negative delta H means that it's an exothermic reaction like it says, so a positive delta H must also mean that it's an endothermic reaction. It says it on the table. We can also investigate entropy changes by comparing the phases before and after the reaction. All right, ladies and gentlemen, we're gonna take a look at a couple of reactions on table I. Shu, are you ready?
I'm ready.
All right, so our first reaction is carbon solid plus O2 gas yields CO2 gas. We've actually already given you some arrows as to where these are on table I to help you find them. So let's find that reaction and let's figure out its delta H value.
All right, so for that first one, it looks like my delta H is equal to negative 393.5. My units at the top are kilojoules.
Okay, and just to reiterate, what does that negative sign mean on the delta H value?
Well, it says right at the bottom, but I knew this anyways. If it's a negative sign, that must mean that it's an exothermic reaction.
Okay, good. Let's also establish that these are molar quantities.
Okay.
Right? So, and it's per moles of product. So in this particular balanced equation, how many moles of product do we have?
Well, I just see that there's a CO2, so sort of an assumed one. That could be one molecule or 1 mole, right?
That's right.
Okay.
Okay, so this is kilojoules per mole, so we're dividing here. So what would my kilojoules per mole be for this particular reaction?
All right, well, so it's just 1 mole of the CO2. So it would just be the same number, negative 393.5 kilojoules per mole.
Very good. All right, one last thing here. Let's take a look at the phases of this chemical reaction and what we're going from and to, and let's kind of discover what's going on with entropy.
Okay, so I've got a solid and a gas on the left, and I've got just a gas on the right.
Okay, so remember, entropy is the randomness or disorder, so what's happening to the entropy as we progress from left to right through this chemical reaction?
Well, I do have a gas on both sides, but it's a solid and a gas on the left to just a gas on the right. So I would think since it's only a gas that we're getting more disorder, so the entropy is increasing.
That's correct.
All right, so entropy increases.
Very good. Let's take a look at another example here. We've got 4Al solid plus 3O2 gas yields 2Al2O3 solid. Let's get this delta H value as well.
All right, well, this one is right down below, and this one is also negative. It's negative 3,351 kilojoules.
Okay, let's also make this one a molar quantity of our product. So this one's a little bit different. Let's see if you get this one.
Well, it looks like there's a 2 in front of the product of Al2O3, so I think I have to divide by 2 moles of the Al2O3.
Very good. You got to be careful here because not all of these are in 1 mole.
Right, okay. So when I do that, I get negative 1675.5 kilojoules per mole.
All right, good. And one last thing, let's check out the entropy by looking at the phases.
All right, so I've got a solid and a gas on the left again, but only a solid on the right. So since I'm going to only solid, that's actually more ordered, less disordered. So the entropy is decreasing.
Good, less disordered, entropy is decreasing. Very good.
All right, we're gonna break down table I a little further. We're gonna start with combustion reactions, which are found at the top of table I. Well, how do we know they're combustion reactions? Well, we have a reactant combining with oxygen on the left, and then over on the right, we have products of carbon dioxide and water every time. If you take a look at the delta H values, they are all negative. Combustion is a reaction that is always exothermic. Let's take a look at that last reaction. It's glucose being combusted. So we again know that delta H, the enthalpy change, is negative because of the sign here. And if we're looking at entropy, entropy, by the way, is labeled delta S. We just have to look at the phases. So we've got solid and gas on the reactant side. We've got gas and liquid on the product side. So clearly our entropy is going up. So we say that delta S is positive.
Continuing on table I, the next batch of chemical reactions we have are synthesis reactions. Now we know these are all synthesis reactions because we can see 2 small compounds or elements are combining to form 1 larger compound. So these are all synthesis reactions. Now looking at our column for delta H, one thing we should notice is that we have a good mix of positive and negative delta H values. So some are endothermic, some are exothermic, so you gotta be careful and pay attention to the sign. If we take a look at the example with the arrow, we have N2 gas plus 2O2 gas yields 2 NO2 gas. That has a delta H value of plus 66.4 kilojoules. So it's positive. A positive delta H means that I am endothermic. Okay? Looking at the phases of this chemical reaction, I've got gas plus gas gives me more gas. Everything's gas. So the phases aren't going to help me here. I have to dig a little deeper. We're going to take a look at the total number of moles. Okay? So I have 1 mole of N2. I have 2 moles of O2. So I have 3 total moles of reactant. I only have 2 moles of product. So the total moles went down. Therefore, my order, I increased in my order or I decreased in my disorder. So my delta S value is negative.
Continuing on with table I, we have dissolving. Notice that we have ionic solids on the left, and over our reaction arrow, we have water. That means we're adding these ionic solids to water and dissolving is occurring. Now technically that's not a chemical reaction, it's a physical change, but we still list them amongst other reactions on table I. Our products are aqueous. The ions are dissociating in the water. Now in terms of delta H, we have both positive and negative values, just like we did for the synthesis reaction, so just be careful, make sure you're looking at your delta H's carefully. Let's further analyze NaCl solid dissolving in water. We have a positive delta H, so enthalpy change is positive, and we're going from solid to aqueous. Aqueous is just like liquid, so we are getting more disordered. So we say that delta S is also positive.
Our final reaction type on table I is neutralization. Now this is just a general formula showing the H pluses or the hydronium ions reacting with the OH minus ions, your hydroxide ions, to form water. All right, our delta H value of negative 55.8, so we have a negative delta H value. All right, and if we look at our entropy or our delta S value for this reaction, we're going from aqueous to liquid, and we kind of want you to look at aqueous and liquid as being pretty much the same. So we got to look at moles again. All right, so we have 1 mole of H plus and 1 mole of OH minus, so that's 2 on the reactant side. I'm going to 1 mole of water, so my overall disorder or entropy is going down, so it's a negative delta S value. You try number 1. Use the equation above to answer the following. A, is this reaction endothermic or exothermic? How do you know? B, is the entropy increasing or decreasing? How do you know?
Spontaneity. Intro. A chemical reaction that is spontaneous is often thought of as occurring with no outside force. Spontaneous changes are not necessarily fast though. Another way of thinking about a spontaneous change is that it is the preferred direction. In other words, the reverse reaction is not favored of the two directions.
Remember that changes that go to low energy, exothermic, and high entropy are favored in nature. Thus, these reactions tend to be spontaneous.
All right, if we take a look at the images below, we have a little seesaw, and on the left we have entropy, and on the right we have enthalpy. Well, when entropy goes up and enthalpy or heat goes down, our seesaw tips to the right, we get a green reaction, meaning go, this reaction does occur.
In turn, changes that go to high energy, endothermic, and low entropy are not favored in nature. Thus, these reactions tend to be non-spontaneous.
So looking at our seesaw again, if the entropy goes down and the enthalpy or heat goes up, our reaction's red. That means stop. This reaction does not occur.
Gibbs free energy equation. Not that Gibbs, no relation. The degree of spontaneity of a reaction can be found using the Gibbs free energy equation found on table T. Looking above, that equation is delta G equals delta H minus T delta S. To review, delta G is free energy, delta H is enthalpy, T is temperature, and delta S is entropy. We will use this equation qualitatively to determine if a reaction is spontaneous. When delta G is negative, the reaction is spontaneous. When delta G is positive, the reaction is non-spontaneous. When delta G is 0, the reaction is at equilibrium, no preferred direction.
All right, we're gonna kind of delve into Gibbs free energy equation. Again, we're using this qualitatively. We're not subbing in numbers. We're actually gonna look at mathematical signs. Let's look at conditions under which a reaction is always spontaneous. Well, as mentioned earlier, if it's spontaneous, then delta G should be negative. So I'm gonna label delta G as being negative. Now I'm gonna ask myself, what delta H and delta S values will mathematically give me a negative delta G? Well, clearly a negative delta H is gonna help delta G be negative. That's an exothermic reaction, and we've talked before about how exothermic reactions are favorable. That means they are spontaneous. And we gotta be careful with delta S because there's a minus sign in front of the T delta S. So we have to think of what times a negative will actually help make delta G negative. So mathematically, putting a positive here makes this whole thing negative, which is what we want. Let's use happy faces to remind us of that. So negative, that's favorable. Happy, making it spontaneous. And then overall, positive times a negative is negative. Happy, that helps us be spontaneous. Now, what does a positive delta S mean? This means that we are increasing the entropy. Again, this is something that you already know. We've talked already how an increase in entropy is favored in nature, and so therefore it favors a spontaneous change. Next, we're going to talk about conditions under which a reaction is never spontaneous. So never spontaneous, non-spontaneous, what I like to call non-spon, that means delta G will actually be positive, not negative. So we're thinking of conditions under which delta H and delta S will lead delta G to be positive. So clearly a positive delta H is going to lead to a positive delta G. Now this is an unfavorable condition. We don't like reactions to be endothermic for spontaneous changes. Add my sad face, that doesn't help this reaction be spontaneous. It makes it non-spontaneous. All right, be careful with our negative sign. So it's minus T times something else. So if delta G is going to be positive, we want this other term to be positive. So a negative times a negative mathematically creates a positive sign, and a positive sign here is going to help delta G overall be positive. Again, overall, this is not favorable. That's not going to help this be spontaneous. So delta H being positive, that's endothermic, right? That's not favorable. And delta S being negative, that's a decrease in entropy. That is also not favorable. So overall, this reaction is non-spontaneous. Okay, so far we've talked about how a reaction can be always spontaneous, in which we have delta H being negative and delta S being positive. Notice they have opposite signs. We've also talked about how a reaction can be always non-spontaneous. Delta H is positive in this case, and delta S is negative. Again, opposite signs. But what if they both have the same mathematical signs? Now it's a little bit more ambiguous. We're going to start with spontaneous at low temperatures, and for this, we have both delta H and delta S being negative. So what's going to happen here? Well, it says spontaneous at low temperatures, so we know that delta G should overall be negative. But let's break down the delta H and delta S terms. Delta H is negative, that's going to help delta G be negative. So we get a happy face there, right? But negative T times a negative delta S, that overall is going to be positive. That's not going to help delta G be negative. So we get a sad face. So one factor is favorable and the other is not. So how are we going to overall get this to be spontaneous? Well, what we want to do is overall have our happy face, right? Delta G has to be negative. So what we want to do is we want to minimize our sad face, minimize the sadness so that overall we are happy. The way we're going to do that is at a low temperature. If I lower my temperature, I'm actually getting a smaller overall value for that entropy factor, and it helps me minimize the entropy. And in doing so, that helps the delta H being negative to dominate and overall make delta G negative. All right, so what about spontaneous at high temperatures? For this situation, both delta H and delta S are positive. So I'm going to put in my positive values. And it does say spontaneous, so overall delta G is going to be negative. Let's break down delta H and delta S. Now delta H is a sad face, that's unfavorable, because delta H being positive is not going to help delta G be negative. Over on our T delta S term, negative times a positive is overall mathematically negative. That is a happy face. That is favorable, and it is going to help delta G to be negative. All right, well again, one's favorable, one's not. What we're going to want to do now is maximize our happiness on the T delta S term so that overall we are happy, not sad, right? So how are we going to do that? Well, we're going to raise the temperature, high T, because when I raise the temperature, I'm going to overall help that term be more negative, and it's going to maximize my entropy term. When I do that, it helps minimize the delta H, which doesn't help delta G be negative, and overall delta G can be negative and therefore spontaneous. Okay, we're going to do an example of applying Gibbs free energy equation. Are you ready, Fu?
I am.
All right. So it says, under what conditions is the above equation spontaneous? Let's write Gibbs free energy equation first.
Okay. Delta G equals delta H minus T delta S.
All right, it says in the question that this reaction is spontaneous. So what should the sign of delta G be?
Negative delta G.
Good, let's fill in negative. And now we're looking at a specific equation, so we're gonna analyze the delta H and the delta S. So what can you tell me about the sign of delta H given that equation?
All right, well, this looks right off of table I, and the delta H value is negative 3,351, so delta H is negative.
Good, let's fill that in. Does that get a happy or sad face for helping delta G be negative?
Well, negative is exothermic. Exothermic is favorable, so that's a happy face.
All right, very good. So now let's analyze the entropy change from left to right in this particular equation.
All right, so I'm going from a solid and a gas to all solid. So it looks like I'm actually decreasing in my disorder or my entropy, so it's a negative delta S.
All right, so let's fill that into our equation with the signs.
So minus a T, negative.
Now what's a negative times a negative?
Negative times a negative is a positive.
Good, so let's label that those two things combined together are going to be a positive. Is that a happy or sad face? Is that favorable or unfavorable?
Well, a negative delta S there, that's unfavorable.
That is, right? Entropy is going down. Positive is not gonna help delta G be negative, is it? So we've got one condition that's favorable, one that's not. So what condition can we set to help maximize our happiness and minimize our unhappiness?
All right, so since delta H is negative, that makes me happy. I want to minimize that sadness so I can change temperature. So I want a low temperature to kind of minimize this negative component over here. So a low temperature is what I want.
Very good. Low temperature helps make that term overall smaller, which allows us to let the delta H dominate, which is negative, which then in turn makes delta G negative.
Okay.
Good. You try number 2. Under what conditions is the above equation spontaneous? Make sure to use Gibbs' free energy equation in your analysis.
Well, that's going to do it for today's episode on enthalpy and entropy.
It's been emotional.
So, Shu, we've already talked about entropy. We talked about energy in the last episode.
You should keep reading. It's the theme of this episode.
Energy and how that is associated with chemical reactions.
Just do it. Just do it, like Nike said. All right, we're gonna break down table S a little bit further.
Table I.
Sorry. All right, we're gonna dig deeper into table I. I don't like that. Okay, let me just keep going. just like a little thing. That's fine. We're still rolling.
I need a comfier chair. All right, continuing on. Why can't I say continuing?
Continuing on table I.
Maybe I can Frankenstein a 2.
Right, that's
Boom.
Nope.
No.
Because I never hit record. I'm still in erase.
Today's episode is brought to you by Digippliance.
Peaceful progression, smoke alarm, sounds of the rainforest. Wake up to your next fire, calm and refreshed.
Digippliance.
But we never off, always on till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie, like my homies, boys to men, it's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.